Hello, everyone. I come from the Beijing Institute of Technology. My name is Guang-Yu, and I will share our work for you. As we all know, the head-mounted display is frequently used in VR. However, this often leads to such simple terms as nausea, fatigue, and vomiting when users wear HMD for a long time, which is considered to be associated with visually induced motion sickness. This is common in immersive virtual environment and can be explained by the sensory conflict theory, also known as the visual vestibular conflict. Visually induced motion sickness refers to the human vision. This list shows the central and peripheral vision of the retina. The retina can be divided into two parts. The first part refers to the central vision area. This area is responsible for the perception of the salient information to achieve object recognition and identification associated with the what question. And the peripheral vision area is responsible for the perception of the non-salient information to confirm spatial orientation, locomotion, posture, and is also associated with the wire question. The term saliency describes the distinctive nature of an area or object which makes it stand out from its surroundings. And eye fixation can be used to maintain a visual gaze on a salient area in user's view. According to the visual neurophysiology, both salient and non-salient points in the view are classified to accurately match the vision information with the two different areas of the retina. As we know, the visually induced motion sickness is caused by the visual vestibular conflict. The method of the optimization mainly focuses on reducing the cognitive conflict or interposing human factors. The most commonly used method related to the vision refer to the limiting the vision information captured by the peripheral vision area, visual area to alleviate the sense of the contradictory. And we can achieve this by reduce the field of vision and blur the visual information captured by the peripheral vision. This work shows the automatic and continuous changing of the FOV, and this shows that this work shows it's effective in reducing the symptoms of the motion sickness. But users may feel unnatural due to the pitch black display. Blurring the visual information captured by the peripheral area refers to select the depth of the field. This work implements the dynamic types of field blurring, which lets users perceptive images more realistically with an increased sense of depth and increasing view comfort. However, in both these two works, just the central pixels are of a higher perceived density. So this limits the eye movements to only focus on the center of a screen, and will limit the user's spatial degrees of the freedom. Besides, in this method, there are a lot of a large number of points in high-resolution area. Visual information of these points is not salient, but with resolution the same as the salient area, which limits the vision perception. In our study, to reduce the visually induced motion sickness in VR, the salient detection approach is used to predict the user focus, and the real-time dynamic learning based on this salient detection approach is used to keep the salient area in focus and blur the other area, which eliminates the pitch black display and achieves the eye fixation simultaneously. In general, the humans have very sensitive vision, and it's difficult for humans in a virtual environment to appreciate a sense with a constant burning level. In this work, we propose that there is a linear relationship between the speed of the participants' virtual moment and the level of learning of non-salient areas. And this relationship is determined by the dynamic altered sensitive parameters S. So the first experiment implements a just noticeable difference test to find the most suitable parameter. As shown in these figures, the cause is a racetrack, and the same thing is used in the other experience. The track consists of several left and right turns and many traffic signs on the road to show the directions of the drivers, and there are lots of pink walls on the road. Also, there are lots of walls on the road. When the participants are shown the virtual environment, they must drive with the following requirements, drive the car on the road as quickly as must, knock down as many walls in the road as possible, and avoid a car accident to the best of their ability. We will apply the dynamic content aware learning based on our salient object detection. This shows the flowchart of the first experiment. There are totally 8 participants in the first study. During the first experiment, each participant needs to complete totally 8 stages with different dynamic modification parameter S, and verbally reported the critical point when the blurring regions in view becomes particularly noticeable. The value of S was initialized to 0 with a step increase of 0.2, and each change of the S was defined as a stage. In each stage, the participants continuously complete 3 laps of driving. In the experiment, the participant was asked to determine whether the blur levels in the current sense and the previous sense were noticeably different or unnoticeably different. So the just noticeable difference locations could be identified by tracking the transitional position from noticeable difference or unnoticeable difference. Here shows some the result of the first experiment. We can see the average driving speed and the average exposure time. And we also show the the just noticeable difference point. We can see that 5 of them say the locations at 1.2 and 2 participants show the locations of 1.4 and the other and the other participants shows feels no noticeable until the experiment finished. So we designed the S as the average of the 1.2. And S is and the final S is 0.6. And this figure shows three screenshots captured from the racing game screen to show the effect of the value S of 0.6 used in this experiment. After determining the most suitable sensitivity parameters as in the experiment 1, experiment 2 was conducted to evaluate the effects of the sealant on preventing the visually induced motion sickness. The VR device, the virtual sense, and the controller used in experiment 2 was the same as those used in the first experiment. In the second experiment, the sensitivity value of S was fixed at 0.6. The comparison experiments were conducted with different camera settings. Everything in the control conditions was the same as the experimental condition, except that the background blurring was removed. Different from the experimental 1, 40 participants was finished this experiment, and they are divided into 2 groups. And the participants was asked to drive 13 laps. After becoming familiar with the experimental scenario, the equipment and the task, the participants was asked to complete the SSQ, and then they start the game. When finishing each lap, the experiment paused and the participants verbally described their states of the comfort. Then the experiment continued. Here shows some in the second experiment, data are collected and compared based on 5 minors, which are come from the SSQ, the simulator sickness questionnaire. The nausea, the ocular motor, the disorientation, the total severity, and the average time. There shows some result of the second experiment. It shows the average driving speed and the average sequence time. Here shows the result of the data from collected from the 40 participants. It can be observed that after applying our method, there are decreases in nausea, oculomotor disorientation, and the total severity. Participants in the experimental condition suffers from less severity of symptoms than those in the control condition. But there is an increase in the average completion time. So somebody may say that the average completion time means the less means means lower speed, which will also lead to reduce the motion sickness. So to confirm that our method has effective on the reduced motion sickness, and to exclude the exclude the okay, and excludes the cases that the reduce of the motion sickness is caused by the lower lower driving speed. So we remain we further we do other statics to further demonstrate the effective of our method. We remain the intersection of the average time data of two experimental conditions, which is between 71 between 71 and 114, and there are totally 24 participants whose average completion time is in this range. Table 2 shows that the average time is normally distributed, and the table 3 shows that there is no significant difference between this average time. Then we conduct the Man-Whitney test to show if there is a significant difference between two groups for the participants. So we can see that after applying our method, there is a significant difference between two groups of the participants. And this conclusion, we can see our approach can effectively prevent the visually induced motion sickness in a virtual environment and enable users to remain in a virtual environment for a long period of time. But there is a limitations in our experiment. We don't use eye tracker. We just use the silent object detection. We use this algorithm instead of the eye tracker because in our virtual environment there is a high-speed game. So, and our silent algorithm has high accuracy in detect the gaze fixation. So we don't use the eye tracker. So we think that although the saliency may not be granted to predict the eye position exactly, the results seem to identify that it works for a particular case with high-speed sense. So our future work will, I think, will be demonstrated that our method to be a more general method to reduce the visually induced motion sickness. Thank you.